Today, let's learn about the big O notation. This big O notation. So in the big O notation, we want to have two functions. We have Fn and we have Gn. So we say that Fn is O. Yeah. So this is the big O. If there are positive constant C is a constant, and NO such that the Fn, this is the function that we want to check, is less than or equal to C multiplied by the function Cn. And this is for every n that is higher than n0. So n0 and C usually it is a constant, and yeah, this is also a constant which is positive. Positive means more than 0. For example, we have 2n plus 10. So this function, yeah, we call this is Fn, is OGN. So we call this is Gn. The Gn function is n. Now we want to check how we can know that this 2n plus 10 is On. First, we put the equation like this one. So the Fn is 2n plus 10. And then we want to check whether is there any C, is there any constant which is when C multiplied by n, it is higher than equal to 2n plus 10. With this equation, so we can derive, okay, 10 is less than Cn minus 2n. So we can get C minus 2, C minus 2 multiplied by n. It is higher than or equal to 10. And then we can get what is n. N will be higher equal to 10 divided by C minus 2. So we can pick any number, any positive number, or we call it the positive constants. So let's see, I have C equals to 3. If C equals to 3, then if C equals to 3, we have 10, which is 3 minus 2. Okay. And we want to see if n0 is 10. Then yeah, we can have that one. 10 divided by 1 is higher than or greater than 10. Because this condition is true, okay? Because there is a constant in C and there is a constant in n0, so this condition is true. Then we can say that 2n plus 10 is On. Now we can look at the other example. For example, I have n power of 2. It is not 1. Okay. how? Yeah, when we put the equation like before, okay, Fn is less than equal to C multiplied by Gn. So we just put what is the n. N is n power of, and what is Gn? Gn is n. Okay. If we derive it, okay, n is less than equal to C. So the above inequality cannot be satisfied since C must be a constant. So C must be a constant, and this one can be any number. So this one is not valid. Then n power of 2 is not ON. Now let's look at the other examples. We have 7n minus 2. And we have 3n power of 3 plus 20n power of 2 plus 5. And we have 3 log n plus 5. So there is a solution here. So 7n minus 2 is ON. We have C which is higher than 0 and n0 higher than 1. So the equation will be satisfied. So if we have C higher than 0 and n0 is higher than 1, so there is a case where the C equals to 7 and the n0 equals to 1. So because we have the positive constant, then this is okay. The next, three n power of 3 plus 20n power of 2 plus 5 is On power of 3. We have the condition C still be higher than 0 and n0 is higher than or equal to 1. So this condition should satisfy with the constant multiplied by n power of 3. So this condition will be true. You can try with the derivation before. So there will be C equals to 4 and n0 equals to 21. For this log, 3 log n plus 5, it is O log n. So you can also use the log function to check the derivation. We need to have a constant which is higher than 0 and n0 higher than equal to 1 with the following derivation. So we have C equals to 8 and n0 equals to 2. So we can look at this, that the n, okay, the higher is n, so we have ON. The highest order here is n power of 3, and this one is n power of 3. The higher order here is log n, and the big O is log n. So this is the rule. If Fn is, this should be, if Fn is a polynomial of degree d, okay, what is degree d? So we call polynomial with degree d, like this one. Then Fn is On power of d. It means we will drop the lower order term. What is lower order terms? Let's say I have n power of 2 plus n plus 5. So this is the highest. This is the highest degree. And then n is lower degree or lower order. Because this is lower order, and it mentioned that we can drop. We can drop means we do not need to consider the lower order. The next is we can drop the constant factor. So like this one, 5, this is constant, so we can drop it. So for example, use the smallest possible class of functions. If we have 2n is on, it means we can drop the constant. The constant is 2n. You can just say this is on instead of 2n, because this is the constant factor. But is it true if we can say 2n is on power of 2? No, because it is higher degree. This is the higher degree. So this is not true. If we have the expression, okay, we will choose the simplest one. What is the simplest one? Let's say we have 3n plus 5. So the simplest one is just choose the order. We know this is the n, so we have on. We don't need to choose O3n because 3 is constant. So we just choose the On instead of O3n. So this is the big O rule. So we come to one of the analysis. We call it the asymptotic algorithm analysis. So the asymptotic algorithm analysis is, we need to determine the running time in big O notation. So when you already learned the previous section, we have, for example, for n plus 5. Okay. So one of the algorithm, we analyzed it and we got for n plus 5. So to perform the asymptotic analysis, we find the worst case number of primitive operations executed as a function of the input size. So you can calculate the primitive operations, like we have one operation, and then we have n operation, we have two operation, we have 2n operation, and so on. And now, after we have like this one for n plus 5, we need to express this function with big O notation. After we have this one, we just need to make this one to big O. So I can say this is O n. Why? Based on the rule, we can drop the lower order and we can drop the constant. So we can drop the lower order and we can drop the constant. So we can just say that for n plus 5 is on. For example, we say that the algorithm find max runs in on time. Okay, so for n plus 5 is on. Since constant factor and lower order terms are eventually dropped anyhow, we can disregard them when counting primitive operation. What does it mean? So when you do with the previous one, when we count this one, we count the operation. Two operations, two operations, two AND operations, two AND operations, 0 until n operation and 1 operation. Based on the big O rule, we can just drop the lower term and we can drop the constant. Then you just need to pay attention to the n. So if this operation is the maximum or the highest degree is n, so we get approximately with the big O notation, this is ON. So that's the meaning by the asymptotic algorithm analysis. Now let's look at a new algorithm. We want to compute the prefix averages. Okay, what is prefix averages? We further illustrate the asymptotic analysis with two algorithms for prefix averages. So there will be some algorithm for prefix averages. What does it mean? The I prefix average of an array X is average of the first I plus 1 elements of X. Okay, now let's see. I have this formula. AI is a summation of x0 plus x1 plus until xi divided by I plus 1. So let's suppose we have A equals to 2. Then we have x index 0 plus x index 1 plus x index 2 and then divided by 2 plus 1. So we want to get the average of the I element, which is 2. Okay, so it is the average of the second under the second element. And means we have the x0 plus x1 plus x2. So there are 3 elements. We want to make the average 2 plus 1. So this is the total number that we have from the index 0. Computing the array A of prefix averages of another array X has application to financial analysis. So let's see this example. So this is the X and this is the A. So X is the red color, A is the blue, purple. Yeah, maybe I can say blue. So the average is 8. And X is the real value. For example, this is a stock. So if we find a stock of a company, then I would like to see the average whenever we have a new value. So after I have X, so the average of course will be the same with the value. So I have a new value. Let's say this is the first is 21. Of course, we have the average is 21. The second value is 23. So 21 plus 23, the average is 23. And then maybe we can say this is day number 1, day number 2, day number 3, and so on. On the day number 3, the stock is rising into 25. So I want to know the average is 21, 23, 25. What is the average of these three numbers? The average is 23. In the day number 4, the stock price becomes 31. So it means I can just add 21, 23, 25, 31 divided by 4. Now the average is 25. In the day number 5, the stock decreased until 20. So we can again do the summation and average. Okay. So this is the meaning by the prefix average. We will get the average whenever we have a new value. Now, how to make the algorithm? So this algorithm, we have a quadratic algorithm. What does it mean? The following algorithm computes prefix averages in quadratic time by applying the definition. This is the method. And then first, given the S or the sequence, first I would like to check the length. Okay. And then I would like to make the average. This average will be for every single sequence. So 0 multiplied by n. So there will be n times of 0. Now I would like to do the loop for j in range n. If you still remember, this one takes one operation. This one takes one and one operation. So this is one, this is two operation. But according to the big O rule, we can drop this lower order. So we do not need to calculate this one. Because we know that there is n times from 0 until n. So it means there will be n operation. Now this operation will also be n time because we want to get from 0 until n. So this operation will run also n time. What about this? We have another for loop. This is from 0 until j plus 1. So when j equals to 0, when j equals to 0 means it will be from 0 until 0. When j equals to 2, then the range will be from 0 until 2. When j equals to 5, it means the range will be from 0 until 5. Okay. So the worst case scenario for this one, it will be until n. Then we can say this is AND operation for the first one. And when it goes to this for loop, there will be another AND operation. So AND, there will be another AND operation. So we have AND multiplied by N. We have this operation total plus equal to the SI, because this is inside the loop. Okay, then we have N multiplied by N. This is same. And then the last is just making the average. So the average is total divided by J plus 1. So because this is in this for loop, then this takes N. If we look at this process, so the worst case, the worst scenario for this prefix average is quadratic. It means we have 1 and 2 for loops, and it will run in the maximum is n power of 2. So the running time of the prefix average 1 is O, which is from 1 until n. So the sum of the first n integers will be n multiplied by n plus 1 divided by 2. So that's a simple visual proof. Yeah, you can see this one. If you have 1, okay, so you have 1 time operation. If you have 2 values, you have 2 times operation. If you have 3 values, you have 3 times operation, and so on. So it means this is quadratic, and the prefix average 1 runs in quadratic time, or O n power of 2. Now we can have another algorithm. It seems it is better because we have only one form. So the following algorithm uses an internal Python function to simplify the code. So what is the internal function? In Python we have sum. So instead of using the for loop, to make the total, this function uses the sum function by. So what is the meaning by sum function? So we have the S from 0 until J plus 1. Do you know what does it mean? S 0 J plus 1. So S is the sequence. Okay. So this line is the same with the previous one. This line is the same with the previous one. Now we have for loop from J0 until N. So it is N operation. Now you can see the summation. What is this one? We want to do the summation from index 0 until J plus 1. So if J equals to 0, then the summation will be from 0 until 1. If J equals to 1, then there will be a summation from S index 0 until 1 plus 1, which is 2. When J equals to 2, there will be a summation from index 0 until 2 plus 1, which is 3. If J equals to 3, then there will be a summation from index 0 until 3 plus 1. And then we will divide it with the J plus 1. It means we will do this summation until j. J is an index which is from 0 until n. So there will be n time for this summation. This summation will be n times and it will run with the for loop for n time. Even though it is looks better or looks simple than the previous one, but the algorithm still run in O n power 2. So this is the first n operation and this is the second n operation. So n multiplied by n, we have n power 2. How about this one? So this algorithm is the same. We want to have the prefix average, but it is in linear time. Why it is in linear time? Let's look at the code. This is the same. We have the statement to get the length, and then we want to set up the A, and then we want to assign total with 0. So it is a for loop. This is an operation. Now you have the total plus equal to Sj. If you know this all kind of operation, it is a primitive operation. So this is the same with the total equal to total plus Sj, something like this. So it is 1, 2, 3 operations. So there will be not more than 3 operations. And then we have this formula. This is 1, 2, 3, 4. So it is only for primitive operation. Because this is a constant and lower order, we can just drop this one. It means this n will have only n operation at the worst case. That's why the prefix average tree runs in ON time. Okay, so you can see the prefix average 1 it runs in ON power of 2. Prefix average 2 runs in ON power of 2. The prefix average 3 runs in ON. Okay, which one is the best one? The best one is the smallest one, which is ON, because it can run in linear time. The prefix average 1 runs in quadratic time. The prefix 2 runs in quadratic time. But the prefix 3 runs in a linear time. If you are the company person, of course you want to get the algorithm which is running fast. Then you can choose this algorithm. Yeah, when you do your team project, you need to analyze this big O notation. Okay, your algorithm runs in what big O notation. There is another we call it relative of big O. So this relative means like the family of big O. We call it big omega and big theta. So big omega means we still use the Fn and Gn, but we use this omega. Fn is big omega Gn if there is a constant C higher than 0 and integer constant n0 higher than 1, such that Fn is higher than or equal to C multiplied by Gn. In the big O, what is the condition? Fn is lower than equal to Tgn. But big omega, it is bigger than or equal to Cgn. What about big theta? In the big theta, we call there are constant C prime higher than 0 and C double prime higher than 0 and an integer constant n0 which is higher than 1, such that it satisfies this equation. So if it is Fn, if we have the function Fn, then we will have C prime multiplied by the Gn, and then we have another C double prime multiplied by the Gn, and the Fn will not be lower than the C prime Gn, and it will not be more than C double prime Gn. Maybe for the easy understanding, we can just say that the Fn equals to Cgn. So not more than Gn and not less than Gn. So this is the simple intuition. When we use the big O, it means Fn is asymptotically less than or equal to Gn. If we use big omega, Fn is asymptotically greater than or equal to Gn. And if we use big theta, means Fn is asymptotically equal to Gn. Okay, so the word this is less than or equal, this is higher than or equal. In big theta, we can just say this is equal. Then what is this one? 5n power of 2 is big omega n power of 2. True or false? If we use the big omega, means the 5n power of 2 should be greater than or equal to the T constant of n power of 2. Okay, that's one. Okay, then yeah, this is true. 5n power of 2 is big omega n. Okay, so 5n 5n power of 2 is greater than or equal to the Cn. Is it true? Because n power of 2 is greater than or equal to C multiplied by N for any constant higher than 0? Yes, this is also true. So we have the C equals to 1 and N0 equals to 1. What about this one? 5n power of 2 is big omega, big theta n power of 2. Okay, this one, because we have the n power of 2 and it equals to n power of 2, and it is true. So we can, later on, we can try with the derivation. So we get 5 as the constant and n0, 1. So let's see again about this kind of counting operation. By looking at this operation, okay, yeah, this is the Python code, and then now look at the number of operations. So I already put here. So when you maybe in the exam, okay, I will also give a kind of problems like this one. What is the big O notation of this code? So how can you look at the big O? Of course, you will calculate the primitive operation at the first time. Okay, this is primitive operation. This is primitive operation. This is primitive operations. And based on the rules, we can just drop the primitive operations. We have, okay, this is n, because it is a loop. And this is another loop. Then we have n multiplied by n time. So we have this operation. This is simple operation, which is only 2, 1 and 2. So I have 2 and multiplied by n. This is also the same, two operation, but because it is inside of the nested loop, because this is the nested loop, so it is 2 multiplied by n multiplied by n. If we finish this loop, okay, we have another loop. So this is from 0 until n, then we have n line. These operations takes 1, 2, 3 operations, then we have 3 and multiplied by n times. So it is in the form. The last one, it is only one operation. Okay. So you can calculate like this one. So you can do 1 plus 1 plus 1 plus 1n plus n power of 2 plus 2 n power of 2 and so on, and we will get like this. So the total time is 7 n power of 2 plus 8 n plus 4. But when we go to the big O notation, we can simplify like this. We can remove the lower order. The lower order, this one. You can remove it. And we can remove the constant. So at the final state, we can say that this is big O and out. Okay, so this is the end. Let's have a break. I will continue after the break.